This scatter plot compares the parameter counts of leading large language models against the estimated number of synapses in the human brain. While modern models boast trillions of parameters, a human brain operates with over 100 trillion synaptic connections. Media headlines routinely describe these systems as digital brains, but despite being loosely inspired by biological structures, neural networks do not replicate human thought processes. Instead, we are looking at two separate systems of logic. Each operates under its own set of physical rules and mathematical constraints. To understand how they diverge, we have to examine three structural pillars: the hardware substrate, the learning algorithms, and their data efficiency. Analyzing AI as software running on silicon, rather than as a biological replica, allows us to map its actual scaling laws and mechanical limits. To find where those limits lie, we have to look at the machines themselves. Artificial neural networks run on silicon processors, governed by synchronous clock cycles. During a forward pass, data moves uniformly. Every single node calculates and fires simultaneously. Pushing this data demands massive power. Training a single large model requires server farms drawing megawatts. The biological human brain operates on wetware, functioning as an asynchronous system. There is no central clock driving uniform computation. Biology relies on spiking neural networks. Neurons fire action potentials only when specific thresholds are met. This creates network sparsity. Only a tiny fraction of localized neurons actively fire, while the vast majority remains dormant. Thus, the brain operates on a 20-watt energy budget. Silicon compensates with transmission speed. Data moves across microchips near the speed of light, driven by the velocity of electrons in copper wire. Biological wetware relies on chemical ion exchange. These signals propagate millions of times slower than their silicon counterparts. The hardware dictates a permanent trade-off. Silicon achieves blinding speed on dense matrices, paying the cost in massive power. Biology sacrifices raw velocity for energy efficiency through sparse, parallel processing. The algorithms running on these substrates are equally distinct. The primary engine driving modern deep learning is backpropagation. Backpropagation is a global error correction mechanism navigating a topographical loss landscape. After a forward pass, an error is calculated, and a global gradient signal is mathematically passed backward through every layer to adjust weights. To calculate those gradients accurately, the entire network must artificially freeze its state. It cannot process new incoming information while updating. If you feed an AI real-time data without freezing the system, it suffers from catastrophic forgetting. New data pathways overwrite established connections, erasing previously learned information. Biological systems do not possess a mechanism to freeze their networks, nor do they calculate global gradients backward through the brain. Human learning relies on localized rules, primarily Hebbian plasticity. Hebbian plasticity states, cells that fire together wire together. When two neighboring neurons activate simultaneously, the bridging synaptic cleft physically strengthens through local chemical activity. The third, inactive neuron, receives no updates, keeping structural changes isolated. Because updates only happen at specific local junctions, humans learn sequentially and continuously. The brain incorporates new memories without ever halting operations to run a global update. Backpropagation dictates that artificial systems strictly separate training phases from inference phases. Biological systems merge learning and processing into a single continuous loop required for survival. Artificial intelligence systems begin as a tabula rasum, a blank slate. They possess no innate structural understanding of the data they process. An LLM requires 10 trillion tokens to achieve fluency, whereas a child acquires language on tens of millions of words. To learn without context, AI relies on brute force mapping, generalizing by plotting trillions of tokens in a high-dimensional space. Humans require a fraction of the data because they arrive with evolutionary priors. These innate biological structures are pre-tuned over millions of years, automatically processing data like edge detection or facial geometry before a child opens their eyes. Humans also benefit from embodied grounding. While an AI node maps isolated text strings, a biological node processes input within a three-dimensional physical environment. Continuous sensory motor feedback, gravity, touch, and spatial awareness physically grounds language in reality. A child understands the word drop because they observe gravity acting on an object, not because they read the word next to fall 10,000 times. This grounding enables few-shot generalization, the capability to understand and apply a highly novel concept after a single exposure. Physical interaction provides a dense set of constraints. By experiencing the weight and resistance of an object, the brain can immediately narrow down how that object functions, forming a stable concept. Through massive data scale, artificial intelligence constructs a comprehensive high-dimensional syntax map. Human cognition uses innate priors and physical constraints to build an actionable, causal world model. Artificial intelligence does not replicate human thought. It provides an effective alternative method of processing information. The victory conditions for silicon are clear. AI dominates in scale, parsing static patterns and processing dense data at speeds biology cannot match. Humanity's substrate yields different advantages. Biology excels at continuous dynamic adaptation, energy efficiency, and extracting reasoning from chaotic environments. The next frontier of hardware engineering is looking back toward biology. Researchers are currently developing neuromorphic computing and liquid neural networks. The focus of this research is to import localized, biological constraints directly into silicon hardware. The goal is to bypass the severe energy and global gradient limitations of backpropagation. Achieving artificial general intelligence will not be the result of building increasingly massive digital brains. It will require understanding and meticulously engineering the rigorous mechanical realities of the biological synapse.